Going. So, good afternoon, everyone, and welcome to this fifth webinar from A2EP and the Sustainable Business Group. This webinar is on commissioning and energy optimisation for aquatic centres. This flows on after previous webinars helping you identify case studies and projects and templates to get a project moving. Today we're going to turn the corner and start looking at how you're going to operate and commission these pieces of equipment. My name is Jarrod and I'm the CEO for the Australian Alliance for Energy Productivity. And I'd like to commence this webinar by acknowledging the traditional custodians of country throughout Australia and their connections to land, sea and community. And I'd like to pay my respects to the elders past, present and into the future. Just to let you know, this webinar is going to be recorded and that the recording and the slides will be sent out to you in the coming days. We're certainly hoping to have a nice interactive session today. So if you've got some questions, hit that Q&A box and type that in, or upvote somebody else's question if you like it, or feel free to have a chat on the sidebar in the chat box there. For those of you who don't know, A2EP, we're a non-for-profit organisation with a lovely broad spectrum of members. And these members share our vision of improving energy productivity and decarbonising Australia. And we couldn't do this and the work that we do without the fabulous support of these members. I'd like to thank them there. Joining me today from the A2EP team, we've got Brendan Voss, project manager and HVAC and chiller heat pump expert, as well as joining Brendan and myself. We've got Alan Pears. He's our technical advisor and a fellow from RMIT and all-round energy efficiency expert. Welcome, Brendan and Alan. I'll bring you into the conversation shortly. And a quick update for everyone joining in that there's lots of resources available. If you go to A2EP and go to our aquatic centres area under our work, you'll find lots of the publications and estimating tools and webinars to help you out in your journey, all there ready to go. This is our fifth webinar. We've been working on these now for some 4 or 5 months. And all of these are available. Again, it's either you'll find them on YouTube or on our website. But yeah, we started off with looking at case studies and let you know that if you're embarking on a journey for heat pump, if you're aquatic centres, you're not the only one. It's been done before. We went through templates for feasibility studies so that you were able to properly specify and help you specify the project that you want to be successful. After that, we went through upgrading economics and myth busting. There's a lot of misinformation out there about how heat pumps work in things like cold climates. You watch that webinar, we'll certainly convince you there's no problems there. And the last webinar we had 2 weeks ago was taking a deep dive into heat pumps, getting into the details, going through the refrigerants and the way they operate and a lot of the different issues you may encounter. And yeah, there was certainly a lot of enjoyment. People really appreciated that one, and it gives you a really good deep dive into heat pumps. We also had a presentation from Anita Rowley at the federal government, who took us through this Community Energy Upgrade Fund. And that's really what we're here for, is to help you get those funds and make sure you've got the support to run a really fabulous upgrade project. And so today, yes, we are talking about commissioning and operating and optimization and maintenance of a heat pump. No use just putting that purchase order out there and be happy with that. You've got to be prepared for what's to come afterwards. So we thought let's focus on when you're getting that heat pump to site and make sure everything's well specified and you have an understanding of what's going to happen there. So joining me here today is we've got a couple of speakers for you. Peter Collins from SEEITEK and Mitchell Birtles from Rheem. We're going to kick off with Mitchell Birtles from Rheem. Mitchell has been working within their heat pump division in Rheem's thermal division for many years, has worked on a lot of different aquatic centre upgrades. I don't think you'll find a company with more references for pool water heating and what have you around Australia. So we're in absolutely very good hands here. Mitchell, if I could ask you to start sharing your screen and yeah, take us through what happens when that heat pump comes to site. How long is this going to, how do we go through this installation and this commissioning process? Mitchell, over to you.
Sure. Thanks a lot for the introduction, Jarrod. It's really great to be a part of the webinar. Sharing the screen with some smart people. It's a good place to be. As Jarrod suggested, my name is Mitch, and I've been working with Rheem for a good few years, supporting design and specification of hot water heat pumps into mechanical and pool industry application. Our team, we specialize in supporting right product solutions and best fit across the board. To get things underway, I'll provide a quick snapshot of the importance of factors occurring pre-installation, as these lead directly to what happens on site when you get to the installation and commissioning and on-site maintenance and that kind of thing. Once we have the right pool heater on site, we need to ensure it's going to do what we say as the manufacturer that it should. It's going to heat the pools. That's the main job it's there to do. We need to be confident that's what's going to happen. The last point's impacted by the effectiveness of that installation, commissioning, and planned maintenance procedures. And getting these right will provide enduring confidence in the pool heating systems for years to come. It really is important for councils to understand the impacts of effective and ineffective pool heating, especially when it commands as much energy of your energy demands as swimming pools do. Most will know by now that a heat pump commands a far higher coefficient performance versus a gas boiler. Heat pumps can be upwards of 6 times more efficient in this space. But even with the most efficient heat pump units, if the factors of selection, installation, and commissioning are not accurately undertaken, you won't be getting the most out of your investment. As the council making your final decision, you will need to consider the input of multiple touch points to ensure you get your project right. It should be clear that accuracy of the initial selection is imperative and requires many inputs. You can't take a one-size-fits-all approach to aquatics and pool heating. Knowing what's involved on each installation is vital. The necessary information isn't always packaged up and ready to go for you. You need to make sure you get the right answers, and that involves asking the right people and validating their information. Queries could come through many streams, but the main 3 that we encounter are the council, obviously, through project or facility management, the hydraulic or mechanical consultant that's been engaged by the council, or the maintenance specialist on site keeping the units running on the daily. Each of these streams ask different questions. They need different answers, and usually they only hold 1 or 2 keys to some of the answers for us as a manufacturer to support. From a council perspective, considering the inputs from the left side of the graphic and the advice from the consultant specialist stream, as well as the supplier, can really make all the difference to the end of the project. To use a baseball analogy, we need to be covering all our bases. We as the consultant, we as the specialist, we as the supplier, and we as the council, so everybody has input in this place. As a supplier, knowing the ins and outs of what's involved on each installation is vital, and each party will bring their relevant set of information. The worst possible outcome is having something come at you from left field that hasn't been taken into consideration, causing major problems, delays, and additional costs on site. The council should offer advisement on the guidelines of the specification based on their general needs. They may have an aquatic center with 3 pools that all need different temperatures, designed for a specific season of use, tailored to a specific set of parameters, and they may need sound efficiency or environmental impact factors built into the design. The specialist can offer the dedicated information specific to the site, like the existing plant type, dimensions of plant rooms they've got, restrictions on site, the overall pool dimensions, what design parameters we're looking at, what temperatures we need, what existing flow rates we have and plan on site, as well as the overall power supply that we've got to work with. The consultant will use their expertise in aquatic center design to frame the requirements of the council and the advice from specialists to deliver that specification to tender. At any point in the conversation, suppliers can be engaged to offer design support for heating. So effective communication from each point really is the key to understanding what your requirement is. So why are these points important? And how does that have an impact on your installation and commissioning? The selection that we as a supplier provide is foundational to the installation work that needs to take place. If we're designing for a new site, as an example, the chosen unit's water flow requirements will dictate a water pump and pipe sizing, electrical requirement, and the overall space needs that you're going to need to consider. If we're working on a retrofit, Have the site conditions changed from the initial install? What's being replaced and why is it being replaced? And are there new regulations that need to be met for this installation? All those factors will dictate what happens during the installation phase. Like I said earlier, one size doesn't fit all with these projects, and it makes real sense to ensure we've actually gotten it all right before we get to the day of installation. So when it comes to getting the unit on site, first we need to consider a few you may consider to be obvious things, but you might be surprised that these things are often overlooked. At this stage, you need to be confident in the skills of the project manager, the plumbing contractors, your electricians, and the supplier's data accuracy. You should be confirming the unit matches specifications signed off during project design phases. It can be really costly if you get the unit in position and find out something's wrong. It's probably best to check these kinds of boxes before a unit gets craned off a truck. Have local factors been checked, like delivery planning, street closures, crane coordination, general site safety, and site shutdown needs? Is the crane that you've got there ordered capable of lifting and booming the unit to its location? That can be an expensive problem to learn about on the day. Part of site location incorporates design and clearances for airflow, which are vital for a heat pump operation. And we tend to look at this factor quite a bit in design phase as the manufacturer. If the unit is going to be enclosed, has the plant room been louvered, and has that plant been cleared by the manufacturer as acceptable? Access to the plant rooms are important. A lot of the time we're installing units in locations that aren't easy to get to. They might be in a dedicated rooftop plant room as an example. Has the site ensured there are compliant safety ladders and means for contractors to safely access these plant areas? If they're on ground level, has there been adequate consideration made for water drainage so we don't run into water pooling issues in plant rooms? Now, once the site location has been confirmed, it's important to ensure the power supply is suitable. And do we have the relevant people at the ready to perform their tasks so that we're being as efficient as we can in the project delivery on the day? It can be really frustrating for contractor and client, and sometimes it can be quite expensive for trades on site to be waiting for one another. One overlooked bit of information, and something we see quite often, is the timing and use of pool blankets. When we run specifications, if pool heaters are designed into the spec and there's no consideration to use them on site, it will impact the overall performance of the system. So we really need to consider that they're ready to go. When commissioning a heat pump, the main consideration really is the cost of getting it right the first time. This will ensure effective performance and give you confidence that your unit is delivering to the requirement that you need. In contrast, not ensuring optimal performance can mean you're not getting the correct outputs, and it could be costing you more money and getting overall less output. Depending on the site, commissioning undertaken by a licensed service agent or the manufacturer's service employee can take around half a day per large unit or multiple banked unit install. We're looking at many aspects of system setup and performance, and depending on the unit configuration, we may need supporting experts in BMS controls or have the installers ready on site to make the necessary tweaks to water flow or the like to ensure we've got the correct performance settings. In the middle of the screen, you can see a snapshot of what we look at, which includes electrical inputs and outputs, refrigerant pressures and temperatures, water temperature differentials, and sensor testing. Controller settings that have been adjusted are also important to note too. We keep these files on hand in dedicated project folders to be able to refer to in the event of any site issue, and the site should also keep a copy on hand as well. Periodical testing of system performance and output can be monthly, bi-monthly, or quarterly, but it really should be regular. It shouldn't take much more than a couple of hours per unit with a qualified refrigeration technician or licensed heat pump service agent if all that's happening are the standard checks and balances. They'll be ensuring refrigerant circuit performance, system motor effectiveness, water temperature differentials, the coils and fans are clear of debris. If there is a note the refrigerant has been topped up, or you're advised that the system needs a bit of gas, this is generally a sign of a bigger issue and it really should be further fault finding that needs to be undertaken. It's a requirement of the site to ensure safe and suitable access to these units for servicing, so please ensure these plants are kept clean and clear. Facilities managers can be trained on understanding controls, requirements, and alarm actions, but ultimately, like I said before, any dedicated work should be undertaken by the licensed technicians in their field. Keeping documentation of any adjustments or changes to the initial commissioning points during maintenance is really important. as that may support further fault finding down the track if needs be. If something becomes a little bit more difficult, it's really important for the manufacturer to have everything on hand. Once these units are up and running, maintenance is done, your temperature general maintenance is going to be generally limited, and you should be confident your sites are being effectively heated to the design conditions. Thanks a lot for your time. That's the insight that we've got into commissioning and maintenance and general installation and what leads into that happening on site. Thank you.
Mitchell, thank you so much. And if we've got some questions for the audience for Mitch, feel free to put that through, and we'll monitor that one. Mitch, I think I'm glad we're recording this. There was a lot of good points there, and I didn't quite keep up. There's it feels like we might need there's a checklist is really needed for that installation. But yeah, this is about professional project management, but lots of excellent tips there. Do you guys have a checklist, like a pre-commissioning checklist that you utilize to say, make sure that we've got access and things like that?
We have 2 lots of commissioning checklists. So we've got like a pre and during checklist. So we'll make sure that we've got sort of our checks and balances in order. And we spend a lot of time working with the sites to ensure that we're getting the unit delivered in such a way that the cranes are going to be meeting them on time, working with the person doing the installation or the project manager so that we're covering those bases. So we've got the sort of the pre-commissioning checklist and the during commissioning checklist. Yeah,
absolutely. And actually, Alan, go for it.
Yeah, terrific presentation. Thanks. That's great.
Thank you.
I guess I was curious to find out what are the most common shortcomings, shall we say, in this process that you go through that you see?
I think generally at the beginning, it's an issue of oversight when we're looking at the design of the unit itself. We might be looking at something that's, say we think we might need 200 kilowatts or something like that. Someone will come and say with that in their head, and then we'll run through the actual certification and specification of the information that we're given. And that won't be what we need under a specific design condition. So if we're looking to run a system, say, or an aquatic center needs to run year round, we need to be designing for that ambient at the peak condition, which is winter for a heat pump. So while, yeah, you might need 200 kilowatts, that's not necessarily going to be a 200 kilowatt heat pump. And that's a big pitfall that people tend to fall into.
I noticed you mentioned pool blankets. I think we're going to touch on that a bit later, Alan, when we talk about energy flows and such an important part of that energy mass balance. Brendan, if I could throw to you, we touched on craneage the other week, and I think the point was don't underestimate it, huh?
Craneage? No, never underestimate craneage, because there's always something that stops the lift, delays the lift, changes the lift, all that sort of stuff. So yeah, it's one of those costs to be wary of all the time. Yeah.
Well, lots of planning and no doubt potential for
contingencies.
Yeah,
contingencies, backups, second dates, third dates, backup dates, everything you can.
Yeah,
in the project plan.
Talking thousands of dollars an hour. And if I recall correctly, Mitch, that when Canada Bay had to do something a bit special trying to get their one, certainly that's what the owners of Cabarita Pool, they mentioned that was quite a tricky part of their installation, is getting that craneage right.
Yeah, they mentioned that last week in the presentation that you guys had, I think, from memory. But it can be learned by doing things the hard way sometimes. Like we can run an initial specification on a project, and then the council will run ahead 3 or 4 steps and start planning something. But then if they need something that's slightly heavier and they've already got the craneage organized, once the unit's on site, they may not have the capability to lift the unit that they've got. So rechecking, going through those checks and balances, like I said to Alan earlier, to make sure that we've got the right, we're actually talking about the right unit on site before we get there, is really important.
Brilliant. Mitchell, many thanks for that. I think, again, I'm glad we've recorded this. I think you've given a lot of tidbits in a short time. Much appreciated. That's excellent. And please do stay online if there's any questions and what have you. And join us for further discussion later.
Sure. I try to talk slower, but I tend to be quite a bit of a fast talker. So
done well. Thank you. So hopefully that gives some help when you're going for the grant to make sure you've been really ticking things off to make sure you've got everything covered. As they said last week in the grant, you know, you're going to ask for that money. There's no coming back. You go and ask for your couple $100,000. You can't come back later and say, sorry, my project was a lot more. I need some more money. So you've got to have all this included here. And that's actually what we wanted to talk about next. And this is often overlooked in projects, and that's optimization of the equipment. And it's usually a matter of the end user not actually specifying and asking for that ongoing optimization. It's a case of let's get this in, get this running, tick it off against the performance, and then okay, we'll take it from there. But that shouldn't necessarily be the end of the story. And so what we thought is we'll just sort of explore a little bit about optimization, and this goes for air conditioning equipment and heat pumps. And so to discuss that, we've got Peter Collins from SEEITEK. And Peter, if I could ask you to share your screen, and we'll test that the sound is working. Is your sound working there? Okay, we had some troubles there.
Sure. Can you hear me okay?
Excellent. Peter, as a quick introduction, Managing Director for SEEITEK, absolutely passionate about energy efficiency and energy systems, and has been scouring the world for excellent technology that really provides energy savings benefits. So we thought we'd bring Peter in. Let's talk about ways to optimize your heat pump or refrigeration or chiller system, and the opportunity for energy savings there. Peter, over to you. Take us through the technology.
Thank you, Jarrod, and thank you for the organisers, and thank you kindly for the attendees today. So, as Jarrod mentioned, SEEITEK is energy and asset performance services company. We have a number of products that are really about identifying the issue of energy wastage, but also providing a solution for that energy wastage issue. So what I'd like to talk to you about today is the concept of compressor optimization. So the electric motor in the compressor is the highest consumer of electricity in that piece of equipment, whether it's a chiller, refrigeration plant, or a heat pump system. Now, even with new technologies today, we're still looking at consumption of between 50 to 70% of the total energy of that unit. So we're focusing on that compressor today primarily because it is the biggest consumer of the energy. So essentially in the last 50 years, a heat pump or air conditioning system hasn't changed much. It's a box with heat exchange coils and fans, and pumps gas around the system. So the refrigerant itself, or gas within the system, is continually changing depending on the conditions it's operating with. It's changing temperatures, it's changing pressures. So therefore, the impact is you're having a dynamic impact within your air conditioning system or heat pump. So in other words, if you've got a high load, the swimming pool or the aquatic centre is full, there's going to be a high demand on the system. If it's empty, there's not going to be such a high demand on that system. So when a compressor isn't running, it doesn't use energy. You could just switch the compressor off, and the sustainability manager and the accountant will be very happy because they're saving emissions and money. But the mums and dads and the kids in the pool won't be very happy, and you'll probably be out of business before you know it. So with a dynamic solution, the aim is to reduce the amount of time that the compressor runs for, or that it's loaded for, over and above the mechanical control that has been supplied with that system. There is a proven method of reducing the runtime of the compressor while at all times maintaining the temperature that you want and not compromising the warranty or the performance of that system. What if you could dynamically adjust, or what if you could turn the compressor on, turn it off, load it, unload it effectively without affecting the system, but making it more efficient. Even on brand new systems that have got EC fans, variable speed drives, and all the various controls that you can find in a modern day system. So a retrofit system aims to dynamically adjust the starting and the turning off of the compressor, and it affects how the compressor is working, which basically improves its operational performance and makes it more energy efficient. The downstream effect is that you reduce the amount of kilowatt hours consumption that the compressor is using, while improving the efficiency of the system and not interfering with that space temperature or the humidity, and causing issues with the effectiveness of the system. So thermostats and standard controls that are usually supplied with the packaged systems, they're good at what they do, but they're never really fully concerned with the compressor and optimizing the compressor. They're mainly concerned with making sure that the system doesn't fail, it runs as long as it's supposed to run, and it provides the necessary cooling that it's supposed to be cooling, or the heating that it's supposed to be providing. So the smart cool device is an intelligent controller. It's installed in series with the existing control solutions. So we do not replace the existing controllers within the system that you've purchased. We use the manufacturer-approved touch points and connections. They provide us with the interface cables with which to connect smart cool device or the compressor optimization device to their system. Why this is important is because one of the questions that comes up is, how does this affect warranty? We've got two types of controllers. There's a simple controller. There's a modular controller for heat pumps and chillers. So depending on the simplicity of the system or the complexity of your system, we've kind of got you covered across all bases. The system is absolutely compatible with any of the world's leading brands, Train, Mitsubishi Electric, no issues to warranty. In fact, what we do is we consult with the manufacturers and talk to them about what we're actually doing, just so that they can retain a level of comfort. We do a internationally recognised protocol for testing and measuring the results of an energy saving device on the compressor. The reason we do that is to make sure that we maintain some impartiality in providing the data to the customer, to make sure that they can validate the savings themselves. So which I'll show in some of the next slides, we provide an independent verification of the energy consumption of that system and track that in real time. So I've got an example of a project here. What you're looking at, the line in the graph there is reflective to the ambient temperatures. In the blue there, you have without the smart cool running energy consumption that was monitored externally of the compressor. And then you have in the green graphs there, the impact of the energy consumption when the smart cool is actually switched on. Now, ambient temperatures within seasons can vary significantly. So what we do is we regress that temperature data and provide, as you can see on the right-hand side, a more accurate representation as to the impact of the smart cool turned on and the compressor is not optimized and running within their design criteria. This is just another case study, but different types of equipment. These would be heat pumps, not necessarily aqua heat pumps. Again, you can quite significantly see the energy savings that was determined by the monitoring there. There's two devices. So one is a simple device for, say, a 25 kilowatt standard heat pump, and there's a more complex modular energy saving device, which would be for the more high capacity 200, 300, 400 kilowatt larger systems. In terms of the Eco 3, you'd be looking at around a cost of 5 to 6K fully installed, and about a 2-hour install time with minimal interruption to the existing piece of equipment. With the ESM controller, you'd be looking at 2 days installation and commissioning. There's a little bit more complex work involved to make sure that it's completely compatible with the chillers that it's working with. A single chiller set or a single large heat pump system would be coming in the range of about 55k. For 4 systems, quite a more complex installation, you'd be looking at around 86k fully installed. The technology itself is actually coming back to Australia. It was invented by an Australian refrigeration engineer, and it's been developed quite significantly. So it's nice to be bringing this technology back to Australia. If you do have a site, if you do have some equipment you'd like to, we can do a site assessment and we can provide you a quotation. So what that means is if you've already got your systems up and running, they're already efficient, you're happy with the maintenance, they're operating absolutely maximally, we can come out to site and we can make some recommendations about adding the compressor optimization technology so that we can get some more savings beyond what the manufacturer's savings are.
Excellent. Thanks for that, Peter. And so I understand if the council has a quotation already for a heat pump supply, are you able to use that quotation and say, yeah, here is the cost for this technology to go with that, so that the councils could include that with their grant?
Yeah, so it's quite a simple process. What we do is we will obtain the manufacturer's model details of that particular system. We will analyze its or ascertain its capacity. We can talk to the client, find out how many hours it's running for, has it been maintained, and gather that information. So it's a pretty simple process to put a quotation together, and based on the operating parameters of that system, not only will we just put together a quotation, but we can estimate the energy savings that the client would expect to achieve.
Excellent. And I understand this is going to help with councils keeping their suppliers honest. Like this is almost going to provide like something of a verification that the energy supply was as expected. So it's a two-way thing to help them with the savings and also with that holding people accountable as well. Yeah.
Absolutely. Look, we work with the incumbent site contractor who's maintaining that system. And the reason we do that is we want to help them understand what the system does, what it doesn't do, and how it's not going to interfere with the operation and the maintenance and the various aspects of that site. Yeah.
Good. Just checking if there's any
There is
questions through there. Go for it.
Oh, there is a question. So I sort of have one too, and I think just sort of from Peter's perspective, it's not interfering. So just as like a clarification, I guess, just so everybody is clear, it's not going past the compressor inside the heat pump. It's not changing quantities of water flow, temperatures or anything. It's leaving the BMS basically fully intact. I think that's my question to start, just to get a clarification in there. So.
Yeah, so through the customer connection points or the manufacturer's connection points, we interface with the existing controller. So the primary controller runs the show, basically. We don't replace any of the decisions that controller makes. In fact, if there's a maintenance event or there's an alarm event in that system, the smart call will actually automatically bypass itself out. So it's not interfering with that system. So it's operating dynamically on the load parameters of that system based on what the primary controller is telling it to do. So that it never overrides the primary controller.
Sure. Very good. Another question is, does the control strategy have any impact on life cycle of the circuitry or the components inside the heat pump itself? And probably the flow on is, if it can improve efficiency, then would you sell to heat pump manufacturers? Is the flow on question from that? So
the first part of that question is it does have an impact on the life cycle. Now we know that's an infinite area of different variables, but on a practical level, if you are running the compressor less, then there's less wear and tear on that compressor. So technically, you will be getting a life cycle improvement in your equipment. The question to the manufacturers themselves, a lot of people ask, well, if this is so good, why don't they do it? The manufacturers are tasked with producing a particular product that produces particular outputs, and they have completely different concerns to directly optimizing the compressor itself. So, yeah. And of course, the IP is extremely, it's an extremely tight IP, and it's very well protected.
So, sort of flowing on from that, Peter, there's a question here about how long after, I guess, installation is ideal to have it performed. I think we just said we could do it at the start, but in an ideal scenario for measurement and verification, is there a time period that people should consider? 3 months, 6 months, 1 year, whatever it may be. So,
there's some constraints around that, obviously, with some of the government initiatives, that there's a particular protocol that has to be met. Typically, what we do is a 4 to 6 week period where we run the smart pool on, we run it off, we run it on, we run it off. We independently collect that data and present that to the client. Now, if there is a situation where there's unusual weather events occur, or has been a maintenance event that's occurred on that site, of course we can extend that period. But 4 to 6 weeks is usually sufficient to demonstrate to the customer that this is actually doing what it's supposed to be doing.
Cool. Have you got a typical return on investment? So post that period, like what's typically that look like?
Yeah, and so the variables that are very much determine the return on investment are things like how long the system is running for, how many hours it's running, and of course, what are the current energy costs. So the low-hanging fruit, if you've got a system that's running 24/7 or it's running 15 hours a day, and you're paying 35-40 cents a kilowatt hour, of course, the return on investment is going to be quite high. Now, on a slightly aged existing system, we're optimizing up to 25% additional. You might have a brand new system, we will still get that kilowatt in, kilowatt out. Return on the investment will be lower, but it's still in the 15 to 20%. So, but typically way under 3 years, we're getting anything from 9 months to 36 months, depending on the type of system it is and how long it's operating for.
With such a minimal amount of data and a quick payback period, I think the argument is fairly simple. It's a bit of a no-brainer, isn't it? That this should be something that at least gets considered. Doesn't mean it will in practice. I see Alan laughing, but yeah, nonetheless, it should be considered, I think, all the time if it's delivering such a fast return on investment and requiring quite minimal input, basically quite minimal inputs from the site. So
yeah, and verifiable and provable externally. So you're not relying on us telling you what the savings are.
So there is another curly one, and I know we're going to run short of time, but will you warrant the performance improvement if someone procures it? And what does that look like if someone wants to go down that road?
It comes back to, as I mentioned earlier, the infinite variables. Is the system being maintained correctly? Is the equipment being used correctly? It's very difficult to warrant a continually moving target. So what we do is, with the initial proof of concept of every introduction project, is that we agree with the customer we will reach a savings target of X amount of dollars or emissions, and if we don't achieve that target, then you don't pay for the initial installation. If we do achieve the targets, then we move forward and we start to build a rollout strategy for your business. So there's definitely a lot of protection for the customer there.
Good. SEEITEK putting his money where his mouth is there, Peter, which is good. And yeah, so if I'm hearing you, councils could include this with their grant application. You'd test it maybe a month or two after startup, and then do this month on, month off type thing a couple of times, and yeah, very clearly be able to see the impact of the technology. So great, and again, it often gets overlooked, this optimization a month or two after the installation's done. Things change throughout the year. When the equipment was commissioned, maybe it was only spring conditions, wasn't peak operating, or maybe it was in the middle of winter and it wasn't the shoulder season. So things change, and having a look at that optimization over time is certainly a good investment. So Peter, many thanks for that. That's great to see this tech available, and a 15% savings is nothing to shy at, and that's going to give a lot more return on investment than things like LEDs, or a lot more energy and greenhouse gas savings than things like LEDs. So fabulous. Thank you.
Yeah, thank you. And I again encourage anybody with any further questions or inquiries, please get in touch. Happy to help.
Perfect. Okay, I thought we'd have a quick discussion now on maintenance. Mitchell gave us a little bit on that one, which much appreciated. But given that we do have someone in our panel that's had spent years pulling apart compressors and doing maintenance work, one Brendan Voss, I thought, come on, let's take this opportunity and pick his brain here a little bit. Brendan, you may be probably aware that a lot of councils put in cogen systems in the, let's say 2010s, and for that 5-year period after that, there was a lot of incentives for them to do that. A lot got burnt, and it wasn't just councils; it was hospitals and things like that. They a lot put these in, and a lot got burnt on the maintenance costs, to the extent that they couldn't run them, couldn't get the return on them. It's just such large unexpected costs. How do we compare that to a heat pump? You know, is there some similarities? I'm going to suggest for a cogen system, you might be looking at 5, maybe up to 10% of your capex per year in a bad situation, or more, 30% if it's a major repair, a major rebuild. Can we get near there? What's the safety factors here for a heat pump, and is there any risks with heading down that path at all?
Yeah, so it's an interesting question. So we can get near that percentage of cost, like in a repair, particularly if you have multiple compressors fail, which is often a victim of the system more so than the piece of equipment itself, or as Mitchell pointed out, poor commissioning, I think, or poor setup, or just in general upfront, some of the planning. But the cost quantum is nowhere near as high, like in terms of money, with a heat pump as it is to a typical cogen plant, which is using different compressor technology. It's a bit more, requires a bit more maintenance, I think, than most of the smaller heat pumps would be using in aquatic centers, which are using sealed compressors. So the chance of failure is and wear and tear and need to pull it apart is substantially less. So it would be a less likely to occur, but you still could have, obviously, poor controls could lead to a fairly high bill at some point. So maintenance and obviously commissioning are very important, which echoes Mitch's point from earlier. So
how do we avoid that? How do you ensure that these the controls don't end up with some sort of, let's say, catastrophic failure of a compressor here? And because I'm sure Mitchell's waiting to chime in and say we don't have any problem and this sort of thing. But how do you avoid this?
So we've sort of covered some of the principles in previous webinars, and I think we've hit on it quite a few times. I mean, having enough water volume in the system is a great way to avoid breaking mechanical components, because you're not seeing huge rates of change in temperature, flow. Everything gives you a lot more stability and control. So I think that's obviously a key point. And keeping enough water flow to the unit is the second one. And the third one is just a good maintenance schedule. Like most of the time, the compressor will fail because it pumps oil out of the compressor itself, and no one really knows why that happened at the time, but more often than not, it's controls or it's poor maintenance or lack of maintenance that's made that happen. So those sort of 3 pillars mean if you've got enough water flow and enough water volume and a good maintenance schedule with the right company, the chances are, you know, people have the same compressor running in their fridge, albeit a lot smaller, that runs for 15 years and never fails. So it's a good working example of the same type of technology never failing, basically.
And I'm sure there's alarms, you know, if there's running out of oil, there's alarms are coming up and protections in place before that catastrophic events happens.
There are alarms, and handling those is super important via some sort of system, particularly the building management system, and scaling them. So I've walked into buildings where there's been 1,000 alarms unattended to because they're just scattered alarms that haven't been filtered. So part of the commissioning and setup should be what's a priority alarm, what stops the plant, what doesn't stop the plant, and often that is overlooked as well, basically. So yeah, handling those is important, and not having people just reset them, having them actually implement the root cause. So quite often it's like reset it and get it running as fast as you can, and I would discourage that at any given point without some investigative work. So that extra thermal storage or loop volume means you don't have to rush to fix. You've got a bit more time. So that's why the design is important.
Absolutely. And yet another one there for thermal storage, having that buffer there. Alan?
Yeah, well, I was just wondering, Brendan, I mean, cogen plants have a combustion engine, and the economics seems to be a bit dependent on the difference between gas prices and electricity prices. So are those factors part of the story of the sorts of disappointments people have had with cogen?
Yeah, so from my experience with cogen is failed design initially was the first round. Was a lot of the designs were just inadequate. The second one was people didn't know how to operate them, and the third one was then the gas prices went out of control. So it kind of didn't have a good run, cogen plants. But there has been some running quite successfully and never failed. So I mean, even during that same period. So the gas prices absolutely would play a huge part, Alan, in the economics of that repair as well, because it doesn't make sense to go and reinstate it, right? If the price is so high, and I've seen a number of councils turn them off for that reason. So, yeah. But like you mentioned, the combustion engine part means there's a bit more maintenance than a scroll compressor in a heat pump as well. So
the comment here from the audience about getting a heating and cooling as a service concept. So rather than paying for a package of $1 million for your heat pump upgrade, you're paying a monthly bill for that gigajoules and what have you. Yeah, I expect that is the way that would be typical. That if you hand the keys over and you say, look, I'm going to pay you for heating, not for a heat pump, then you're covered. You know, you're doing all the maintenance unless we were negligent as the council, the operators. And so I believe that is one way. If you want to mitigate that risk of maintenance and what have you, then yeah, heating as a service or cooling as a service will be there. And we had that in our second webinar. If you care to check that recording, you've got a presentation from Stuart Durra from NLX offering that sort of service, heating as a service, to come in and say, we'll take all the capital costs and just charge you, I guess, a monthly fee for that. So absolutely, there's one way that surely you'd get that in the contract to make sure they cover that as well.
We did mention too, I think on the last webinar, it was maintenance and procuring longer extended maintenance programs from the supplier, from the OEM as well, so you can get up to 5 years as well. I think we mentioned in one of our webinars as well. So reducing costs running a 5-year warranty would be another thing to investigate at the start if it's available. As a matter of fact, I've heard people ask for 10. I'm not sure any manufacturer offers 10, but I've seen people asking for 10 years, and in that case, you're probably better off with the heating and cooling as a service type module in that case. But yeah, definitely try and get an extended warranty if you're worried about ongoing maintenance costs, because you are then covered quite well.
I always give that slight bit of warning when you talk about an extended warranty period of 10 years or some sort of crazy bank guarantee. It's like, well, yeah, if the company's not here in 3 years' time, that warranty is not worth a lot. But so yeah. I would prioritize, you know, how often is that? How long has that company been in business and around, and what sort of name do they have? Because I'll vouch that a company like Rheem is not about to walk away from a market and walk away from its obligations. So yeah, I'd go for name over what people write in that warranty, just quietly.
And centers back to our conversation last week about picking the right supplier as well, because you pick the wrong one and they won't warrant it anyway, or they'll find a way out of it, or the contract will have a loophole or something. So it's really important to have the right supplier if you are going to do that. totally agree.
Interesting question come through here. Actually, Peter, while we've got you, let's tackle it, because previously we had talked about load shaving, load shifting, FCAS technologies, and offered by the likes of NLX, Viotis, Flow Power, AGL, and the like. How does your tech integrate with them? I mean, if you're telling the compressor to go when another tech's telling it to slow down because of high electricity prices, what's the theory for integration in that situation, Peter?
The technology operates in isolation on the system that it's connected to. So it's primarily concerned with optimizing that bandwidth where the compressor doesn't need to turn on so soon, and it can turn off a little bit later. So the downstream effect, or the consequential effect of this, scales when you've got multiple systems on site. So if you've got multiple compressors that are now running for less time, that's having an impact on the overall load of your site.
We just lost the sound at the end there, but thanks, Peter. I think that covers that off. Great. If you've got those maintenance questions, hopefully this has given you the prod to make sure you cover that off with your supplier there. We would like to kick it home now with Alan Pears taking us through some final thoughts about your project and how to make sure it's well executed and well integrated. So this is our fifth and final sort of formal webinar. We're going to continue to have some network meetings, but this is our fifth one here. And we thought that let's finish off. We want to just kick it home to make sure that we're doing the best we can to support you to have a good project. And with that, we've got a presentation here from Alan talking about giving an integrated approach with heat pumps and making sure you've got that full understanding of how to integrate this and understand energy flows there. We think this is going to give you that nice little kick home to have a great project. Alan, I'll hand over to you. I'll run the slides for you and let me know when to change them, but all over to you.
Right. Well, you've gone to the first one straight off. Thanks, Jarrod. Yeah, I guess this is kind of my reflections on having sat through quite a lot of interesting sessions that we've had over the last couple of months. So some of it is reflecting messaging that's come through, I think, pretty clearly. And there's a few left field thoughts and ideas in here as well. So for me, the key messages as I've gone on the journey, listening to people and looking at things myself, is to remember that most of the heat that's delivered to an indoor pool is actually lost through the building shell or as hot, humid exhaust air. Because when you think about it, you heat the pool, where does the heat go after it's gone into the pool? So we are talking about a system, and a complex system at that. And that's where another interesting thing, which I'll talk about a bit more later, is that if you can utilize that exhaust heat and the latent heat within due to the humidity, that can actually not just reduce your energy costs because you're recovering waste heat, but also because the heat pump runs at a lower temperature difference with the warmer air, that actually improves its efficiency and increases its heating capacity as well, especially in cold weather. And it's also a way of avoiding icing up in cold weather. And you could collect the water and use it for something else as well. And I think we've had touched on a few times the possibilities of capturing heat from nearby sources or using storage to make a difference. And that's where we've probably talked a lot more about storage, but some people have talked about mining sewers nearby, or there's an example actually in a commercial building where they've put a heat pump in an underground car park, which is a bit like geothermal energy, as well as collecting all the waste heat from the car engines cooling down. So there's lots of interesting possibilities there. And I guess for me, I just keep coming back to this issue that condensation can consume a lot of energy if you're condensing a lot of water on single glazing or other elements of your building, because evaporating water and then losing it is a very energy intensive thing. And anyone who's been burnt by steam instead of just hot water will know there's a lot more energy in water vapor than there is in liquid water. You can also, because the condensation tends to happen on cold surfaces, it means that can be structural components and building materials and things like that, which gives you a maintenance kind of issue that you need to think about. And of course, with Virtles and NLX and others, there's no doubt that energy prices are now varying enormously over the day and over the season. And if you can design your system so that it's flexible, then you can capture a lot of opportunity from where the electricity industry is going, and also from having your own on-site rooftop solar and things like that. Next. Next slide. Yeah. I'm not going to go through this graphic, but as I was reflecting on all this, I kind of have followed aquatic centres and pools since the 80s, and CSIRO were doing really interesting work with solar thermal panels, and a lot of people did put solar thermal heating on pools, then the cogeneration push and all those sorts of things. But what struck me is that an aquatic centre is a really complex system, and if you can step back and not just look at, oh, our job is to heat a pool, you start to see there are lots of energy sources and energy flows. There's interactions between the various systems, and there's opportunity to capture free energy. And all of these things are really, I think we're still in the early days of putting them all together. Next. The pie chart here, you can see, is from 1998. It's pretty old, showing a breakdown of energy use by the various components of a pool. And again, what's interesting here is, yes, heating the pool water, the pale blue bit, is pretty big. And at the same time, that is then evaporating water, which is contributing to heating the pool, and then the pool hall. And again, if you look at the purple bit, the heating, ventilation and cooling of the pool hall in a typical traditional aquatic centre can be pretty big. Then, of course, there's also the lights and the appliances in the cafe and all the hot water and all of those other bits, which are also potentially interacting with the big users. So, yeah, next, thanks. And yes, well, just to finish that last slide, when we move to heat pumps, we just have a whole new opportunity, because when a heat pump's heating a pool, it's producing cool. And this slide that I'm about to talk about compares and contrasts the energy flows through the building envelope of an aquatic centre, of a pool hall, in a really cold day and a really hot day. And what we're starting to see is that we are needing to cool pool halls in hot weather. And one of the council people I was speaking with was saying, well, we've got people fainting because it's so hot, and the pool chemicals are starting to impact on people and things like that. So this again is part of the evolving situation. But what I've done here, I ran a studio with Melbourne University students looking at aquatic centre design, and I developed a fairly simple kind of model of the thermal flows through the pool hall. So we're talking about the building envelope, not so much the pool itself and heating of the pool. And you can see that, you know, basically a traditional poorly insulated, poorly shaded building needs quite a lot of heating and quite a lot of cooling in extreme periods, which is when electricity bills can be high. And as we then upgrade the performance with reasonable efficiency improvements and then go for a pretty good building, we see we can make really quite a big difference in the heating and the cooling energy requirements. And again, this is where we come back in summer. The solar gain through large areas of unprotected glazing can be quite big. So maybe if we go to the next slide then, yeah, I wanted to sort of focus a bit more on the glazing itself, because most of the standard ways of looking up the thermal resistance of single glazing actually assumes that there is a layer of still air clinging to the inside of the glass. And you can see in the two left-hand bars, the dark colour. If you have lots of air blowing over the glazing and you break up that still air film, it actually makes quite a big difference. And I haven't even factored in here the energy waste that's coming from condensation on a cold window. Also, even when you're looking at really good glazing products, which is over on the right-hand side, their thermal insulation performance is actually not that good compared with a well-insulated wall. You know, an insulated wall might have an R2 value, or even maybe 3. But even the double glazed, low emissivity, high performance window is struggling to get an R value of 0.5, which is about an uninsulated wall. So there's plenty of things to think about with glazing, much as architects like it a lot. And there are also glare problems and issues like that some of the operators get very concerned about too, because of safety and so on. The other big issue that keeps cropping up for me is this problem of thermal bridging, because essentially if you've got a metal frame or even concrete, or even a brick wall attached to a concrete slab, you can actually have a lot of heat bypassing your insulation systems. And again, also, where you've got thermal bridges, you tend to have cold surfaces where you will attract the condensation problems. And that will also add to the maintenance issues and things like that. Next slide. Again, going back to my hobby horse about recovering energy in exhaust air, this graph just shows, you can see the yellow arrow showing how much energy you might be able to recover from hot, humid exhaust air if that air is 55 to 65% humidity and around 30 degrees. And in fact, it's more than half the energy that you might recover from that air. So again, I think we need to recognise potential for recovery of a lot of energy and water from exhaust air. Next, we'll get this graph. And again, if you want a practical example of energy recovery from hot, humid air, it is the heat pump clothes dryer. And you can see from the graph on the right that the star ratings of the heat pump dryers are much, much higher than the star ratings of the traditional ones. And in fact, you're looking at up to 75% savings in your energy use from drying clothes, basically because you're recovering the water vapor, the energy in the water vapor, and condensing it out, which is why your heat pump dryer, you've got to always empty the drawer so you don't have water flooding over your floor. Next. So again, one of the interesting things for me is that a lot of people talk about the performance of heat pumps in terms of the ambient temperature. But what really drives the performance of a heat pump is the temperature difference across the heat pump. And that's where you know, bigger heat exchangers, more effective fans, and all sorts of things, and preheating the air that's going into the heat pump can all help you, as well as managing and minimizing the temperature of the water that you're putting into the pool while still getting the heat you require. These are real opportunities. And I think a lot of people kind of have it in their heads that if you reduce the temperature difference by a degree, then that's sort of achieves a couple of % savings. But actually, when you look at the thermodynamics, once you get down to smaller temperature differences, you actually get a bigger improvement in performance per degree reduction. So it's one of these funny things. Of course, the opposite of this is, as we know, when it's really cold, the COP, or the efficiency of the heat pump, can drop off, and its capacity can drop off quite significantly. So paying some attention to just what the temperature difference is really something that I think we can all explore a lot more in the future. Next slide. Okay, then my last slide, and I guess this is sort of thinking about, well, what might A2EP look at in the future? So I think we do need to look at a more integrated approach where we focus more attention on the building envelope and the ventilation rates and things like that, and also how we can do that with existing buildings as well as new ones. I've already gone on about the energy recovery from exhaust. Something that other webinars that A2EP has been running is just highlighting that the rate of innovation in heat pumps and the ways we can apply them, the new ideas that are coming through, it's all just mind-blowing. And that's where, you know, look, if you're looking at data that's a year old, then possibly it's out of date. It's an amazing time, and it reminds me of the problem we used to have with computers, you know, where everyone would agonize, oh, will I buy a new computer now? Oh, no, I know, in a couple of months there'll be a better one that's cheaper. And we're sort of in that bind. So I admire Brimbank and Darebin councils for having a go and getting some pretty good results, and learning what they could have done better and talking about them to the groups that we've been running, because you do have to act at some point, and it's worth keeping in mind that the innovation is continuing. So in that context, keeping some flexibility can be important. And again, I've talked already about just thinking about how can you preheat the air going into a heat pump to help a lot. Mm-hmm. There's a whole lot of things we haven't talked about, like all of the appallingly inefficient equipment in a lot of cafes and drink vending machines and all sorts of things that are around aquatic centres, and lighting and hot water. So there's plenty to look at there. We talked about management of power factor, which is effectively overheating of the electrical wiring and wasting electricity when the oscillation of the voltage and the current are not in the same phase. And that can be very significant. And when people are worried about having to upgrade electrical supply capacity and things like that, if your power factor is poor, one way you may be able to either avoid or reduce the need to upgrade your electrical supply system is to really focus on your power factor. And there's lots of equipment available to do that. Again, I think an important message, and it fits in a bit with this whole issue of the rate of innovation, is that a number of people have found that when they've been upgrading, keeping existing gas equipment as a backup and a support for extreme situations, for example, when it's really cold, that then you can actually save quite a lot on the capital cost of your initial project, while incurring some greenhouse gas emissions, but in many cases not a lot. So there's pragmatic solutions for us to think about as we transition. Again, the whole issue of efficiency, managing peak demand and emissions from outdoor pools is not something we've really gotten onto yet. But the reality I've heard is that quite a lot of councils have got a combination of indoor and outdoor pools, and outdoor pools are quite challenging. So I think there's some discussion to be had there. And then one of the other broader issues that particularly in Victoria we're facing is that on the one hand, we're starting to worry about gas shortages in the middle of winter. We're also trying to get off gas with electric heating, which could increase electrical loads in winter. And then at the same time in Melbourne, in the middle of winter, you can have several days at a time when the rooftop solar output is actually quite low, just when it's coldest. So there's a whole bunch of interesting things for me about where we might go in the future. So I'll stop there. Thank you.
Cool. Alan, thank you so much for bringing all this information that we've been getting across over the last 5 webinars together in that lovely summary. Thank you. I may add a couple little bits and pieces there. You mentioned power factor. That's just a matter of a Googling power factor correction unit, and you'll come up with a bunch of suppliers there. I had this installed at my last factory. Easy to install, easy upgrade. Your site electrician should know about this. That's a very easy one there for you. This one here, I really want to emphasize this one as well. I've read a couple of feasibility studies and in investigation reports for heat pumps, and this is often overlooked. It's you may be looking at electrical capacity, just generally what is the boiler you're trying to replace. But if you've got to look at those plate heat exchangers, it's in that interface. That is so very, very important. A few extra plates in those plate heat exchangers is going to save you a lot of money here. That right now your hot water loop is designed for 80 degrees going out and maybe 60 coming back. A heat pump needs to be below 60, ideally below 60, and that smaller delta T means you need bigger heat exchangers, and the money's absolutely worth it there. And then the final one I'll add on this one here, absolutely so much more energy in the vapor. And so that means whilst a thermal wheel is the product which is often employed to recover energy, a thermal wheel's fine, but that's only getting you a small portion of what's available. If you look at, I think it's a company called Air Change and their Pool Pack Plus system that helps recover heat, latent heat. That'll certainly be a big boost for you there. And feeding that back to that exactly when you need it in those colder days, that's when you want to be as efficient as possible, and that's when that sort of system will really pay off. Alan, thank you so much for that. That's really much appreciated. Okay, I'm just checking to see if we've got any questions in the chat or comments. Brendan, have you been monitoring that one to see if we've got anything come through?
There's none in the box, but I have one because Alan always talks for all this time. I never get to ask any questions, so I'm going to ask a question. How do I, Alan, if I'm like looking at my facility and it's 1 year old and I've done all the right things at design time and I've put nice new whatever, let's say I decide glazing was good and we went down that road and I put airlocks and I did a whole whatever, how do I optimize that as I go or understand if that's changed or something is deteriorating as I go? Because it's all well and good to optimize pumps and heat pumps and whatever, but it's nice. It'd be nice to know that, say, the thermal load has changed or there is a specific area that might have gone off a little bit. So just at a high level, not massive like technical stuff, but just at a general, is there anything people should look for? So
well, I think we're starting to see a number of the BMS providers and other independent suppliers introducing artificial intelligence optimization systems where, they're basically tapping into a lot of data streams, which not only are the things that the BMS might be recording but not doing much with, but also they can tap into, solar radiation or even things like the wind speed and direction. If you've got doors on opposite sides of an aquatic centre, you've got a great suction system to remove air from the building. The Passive House Exeter building had very careful zoning of areas sort of that had similar temperatures to each other within the building layout and things like that. So there's a fair bit you can do, but I think that the ongoing optimization using data analytics is really in its early days. And A2EP actually did a project with UTS and a few others not that long ago on digitalization and energy productivity, and we're just seeing that going gangbusters. And I gather that at the World Economic Forum recently, the big topic was artificial intelligence. And lots of people are worrying about ChatGPT and things like that, but actually a really constructive approach with artificial intelligence is optimizing, identifying early emerging problems, all sorts of things like that. And again, once you get into the AI, I mean, one of the Sydney-based people we've talked with in the past, you know, they are actually identifying early emerging maintenance issues and identifying where they are and what they're likely to be. And they are getting their clients, this is mainly in buildings, getting their clients big savings because they can avoid shutdowns and problems, but also they can tell their maintenance contractor what kind of things they might need to do so they can bring the right equipment and the right people. And I guess probably here, Peter might have a few things to say about where this is going from his perspective. But yeah, I think that's where we're going to go. And again, having flexible equipment that can respond to the information is also very important.
Before Peter, do you have anything to add to that one?
On the data, I picked up on a couple of things there. There's accessing reliable, accurate data, which we call actionable intelligence. You can make some decisions around. There's things you can deploy and put around your facility, particularly around energy. Jarrod talked about power factor, power quality. There's devices you can do that.
We're losing you there, Peter. Okay, Peter, that sound wasn't coming through too well. We might move on. We might come back to you in a minute if we can, but the sound's not too good there. We did have a comment in the come to us, and Brendan's responded to everyone about that. I just thought we'd deal with that one. It's a very, we get this regularly. Looking at large consultancy firms, and they're not willing to innovate. They just rather copy and paste their specifications. And Brendan, I'll let you comment first, and I've got a supplementary comment to that on that issue.
Cool. Yeah, so sort of my comment is quite simple. I mean, it's very common, and it's been common for a long time. And I'm not even going to say it's their fault. There's been a lot of experience, retire, move on, change. The fee structure has changed. What customers are willing to pay consultants has changed quite a lot as well. So there's not really as much end-to-end ownership as there was even when I started in this industry nearly 20 years ago with a consultant, whereas before they owned the project and that was who you went to get your equipment specified and get everything done. And today that has dropped away. So, but unfortunately there is a bit of lack of innovation in some of these places, and I think it's educational more than on purpose. You know, I just don't think the education for some of these up and coming engineers is the same as what it was 15 to 20 years ago, or even many years before. There was always a mentor, and that's what Andrew has mentioned. There was a mentor all the time, and that seems to be a bit lacking. So that's my comment. We try and find the best engineers and bring them into this forum so they can help, but equally there aren't as many as we'd like. So yeah.
I'll add to that and say, well, I used to work for a company that supplied the HVAC and mechanical contractors, and it's known as a very cutthroat industry. It's almost like who can trim the most. And that is sometimes, and they've been working in this environment for 20, 30, 40 years. It's now their culture, and they're now proud of, they're patting on back when they've cut and get that cost down. And that's also a function of their own customers who are treating them cutthroat as well, to say, sorry, you know, we're not paying for innovation. And that needs to change. So the customers, and that goes from councils, aquatic centres owners, and the commercial building owners need to encourage that innovation. It happens. It needs to come from the owners and the ones writing the checks to say, we're going to pay for innovation, but we want you to deliver on that as well. And you're going to hold you accountable to that. And that's one of the reasons why we really wanted to see Peter's technology, SEEITEK. So this is one of those ways you can hold them accountable. Yes, we're going to pay you a little bit more to give us higher performance and innovation. But you've got to deliver on that one. And we know you're going to have contingencies, but yes, you've got to deliver on that one. So that's my 2 cents worth on that one. Good. Just checking out the think there's anything further coming in on the chat there.
There's a lot of people echoing the same sentiment, that the up and coming engineers and their interest in the environment is a great way to get them engaged in the process. I just think it's where they get the experience from, because the old engineers may not want to change, and I think Tony's right there with his comment that the old engineers may not want to change, but hopefully the young guys and the young girls and young people that come through can actually push them to change by saying, we need to care more about the environment, we need to have more innovation, we need to write our spec differently, we need to change, which with the advent of AI, like Owen mentioned, is entirely practical. You see law firms doing things completely differently today than 10 years ago. They're not sitting looking at piles of documents anymore by hand. They've got AI tools to sort them out. So I feel like consulting engineers will eventually get to that point, and they will automate some of the more mundane stuff and perhaps have innovation teams or more time for innovation. But let's hope that happens.
Yeah. I was keen to hear what Mitchell's thought of this session, because clearly you're often probably the meat in the sandwich of some of the issues that are being raised.
Yeah, we are, and we tend to be the conduit a lot of the time to having the right people getting in touch and having the right discussions, so that we can sort of encounter any problems before they get to site. Like I touched on in the presentation, it's really important to get the design right first time. And when we look at what goes into making decisions, a lot of the time, I shouldn't say a lot of the time, sometimes what we get from consultants does seem to look like a bit of a cut and paste. And then we have to work with, sometimes with the contractors or the guys working on the project to deliver the holistic to the job to the council. We have to work through and go, okay, is this actually what the council wanted or needed in their specification, and ask the questions, or get the right people to ask the questions. And then that way we can kind of work with the council sometimes to go, okay, well, maybe it wasn't what you needed because you didn't ask X question or Y question, and then the next 3 or 4 jobs, they're a little bit smarter and wiser for the process.
This innovation doesn't come easy, and it requires champions to fight for it. We saw this in one of our very first webinars we did a couple of years ago. A young man named Ross Kingston working for Brimbank Council, and you can feel the pain that he went through if you watch that webinar to get the heat pumps in there.
Yeah, right.
And it was absolutely worth it, pioneering stuff, but he had to really fight hard and champion for that. And that's sometimes what you've got to do. And as we said, there's this next generation who's going to fight for this better environmental designs. You're going to have these setbacks. You're going to have people trying to say, no, it's not possible. Well, you know, I'd like to think that we've given you plenty of evidence over these last few webinars to say it is possible. You just need to fight for it. And if people need some support with references where they think they're getting so to say, bullied into not innovating, reach out to A2EP, reach out to Alan Pears, and we'll help you through that as well. That's what we're here for. We want to see this go forward. So good. Thank you all to the speakers today. Peter, Mitchell, Alan, and Brendan. It's been fabulous chatting with you today, and really appreciate your presentations. Lots of insights, lots of tips to make successful projects. Really, really appreciate it. To finish off with, we've still got a couple of meetings to go. We're going to do a couple of our network meetings where it's much more interactive, and you can come off and ask questions and get involved in the discussion. And we've got that over the next few weeks, the 29th, next Thursday. We're going to have a run through heat pump cost estimates and give you a bit of a sanity check on some quotations and things you're having. Feel free to come with your quotes and questions and things to that network meeting. Again, very interactive. And then Thursday, the 14th of March, we plan to have a run through. We've got a procurement assessment matrix, and we can help you because you're going to be getting closer to purchasing and things over the next few months. So thought we'd try and help you with that one. Again, trying to guide you away just from looking at that cost and looking for that innovation. We'll hope that will help there for you. Okay. If you are wanting a bit more of a deep dive and want some more A2EP, we have on the 27th, next Tuesday, not far away, we're going to be doing a webinar. We're embracing flexibility to reduce your business energy costs. And this is about designing your equipment right from the start so that you're thinking of a 6 to 8 strategy. How are you going to be looking at reducing electrical consumption of your equipment between 6 and 8 when the sun's gone down and the wind hasn't quite picked up just yet and electricity is expensive? We're going to explore that. We're going to explore opportunities for FCAS and participation within that market, that frequency services, ancillary services there, and so opportunities there. If you've got using large amounts of electricity, you can utilize that and get some really good dollars for turning that off at the right time. And then on the 6th of March, we have Dr. Corden Apagaus from Switzerland, world-renowned expert in high-temperature heat pumps. This is one of A2EP's most favourite webinars every year. It showcases the latest that's happened in research and development demonstration projects over the last 12 months right around the world. It's a global review, and you'll see some really exciting stuff happening. And as Alan mentioned before, it's moving quickly, just like the laptop or the computer analogy, Alan. It's moving really quickly, and so it's great to get an update of what's happening there. That is all from us today. Thank you so much for joining us. A survey is going to pop up right at the end of this webinar. We'd love to get your feedback. We use that in our future communications and programs and things like that. So if you could hang around for a moment and complete that, that'd be much appreciated. Otherwise, a big thank you for joining us today. And we look forward to seeing those who want to join the network meetings next week. Thanks all, and have a nice afternoon.